My name is Dr. Shobbusha. I am the Dean Research and Development of GIS College of Engineering. But herein I am here to talk about my physics courses. Okay, I am basically a physics teacher. I do take physics in the classes in the BTech courses, so first and second year. So now here I am talking about my second year courses, which is called Physics 2 courses. Now, second year course in Physics 2 is separate for separate branches. For computer science and IT, bokeh is something. For mechanical, civil, it is different. For electrical, electronics, all are different. Obviously, they are learning in a different semester. Now, it is stream specific. It is as per the requirement of your own subject. Okay. Say in the computer science and IT syllabus, we have added the latest computation like quantum computation. Like the applications of latest materials called nanomaterials, how the storage and display devices works. These things are not so much connected with the mechanical and civil engineering, who are also learning physics 2 in this course. So we have kept courses like the ultrasonics, okay, which is applied in mechanical and civil. The concept of building acoustics for civil, which is not needed for you. So basically, we have made it stream specific. We made a thorough analysis of the requirement of your course from your department, from your alumni, from the existing student. We made a survey. Based on that, course objective and outcome was framed, and let me present the same now. Now the course objective of this Physics 2 course for CSE and IT student is to introduce topics, okay, is to apply quantum mechanics for learning the latest of computation called quantum computation, learn quantum logic gates. Is to, as a student, you get comprehend about the hardware sectors of your devices, okay, the storage, display part, and also the latest storage devices. The entire electronics is moving very fast, and that is because of the revolution in semiconductors and now the nano devices. Okay, so an introduction to that. So that will be another objective of this course. And also this entire communication system, okay, it's based on the electromagnetic theory. Okay, so we'll also provide you some glimpses of electromagnetic theory, because later on you have got courses on the analog communication and digital communication. Okay. Now the major course outcome of this Physics 2 course for CSE or IT student is that after undergoing this course, you will be able to explain the electromagnetic theory with your basic knowledge of electrostatics, magnetostatics and electromagnetic theory. You will be able to explain the most modern computing devices using the latest idea of quantum mechanics and quantum mechanics principle. You will be able to explain the operation of the most modern storage devices, how it evolved from the magnetic storage to semiconductor devices. You will be able to judge the requirement of the latest material for the purpose of computing, for the circuit design, and for the storage material, that is the ideas of nanomaterials. Okay, so let us, and this is closely connected with your own program, so you can get that in the course outcome, program outcome mapping also. On the screen you can see the various modules that are present in this course, and you can also see the module that we will be starting with. We'll start with one of the promising modules of the course, as well as you can also see the topic that we will begin with. And in this particular class, whatever we'll be focusing on, the related prerequisite, what is the objective of the class, and if at the end of the class you're supposed to get something from me, that is the outcome of the session. So that session outcome also you can see on the screen.
Hello and welcome to class 12 of my series of classes of Physics 2, and we are still living in quantum mechanics 2. Now what we did so far, I have made if you see the last few days of the classes, we are now trying to wrapping up the topic of quantum mechanics 2. We made a final summary of the major points, which is called as the postulates of quantum mechanics. The first postulate gives you the concept of a function. Second postulate gives you the concept of operator. Third postulate gives you how you use operator to get any physical information out of a function. Fourth postulate gives you the idea about average value in quantum mechanics. So, and the fifth one is the acceptability about wave function. Suppose after solving Schrodinger equation, whether you accept a given function or not. That is the last postulate. So essentially, our life is more or less mathematical because our matter is a function of mathematics psi. So we get it by solving a differential equation called Schrodinger equation. After getting psi, dealing with psi, that means you do more mathematics, and more mathematics means you use operator, get physical data. So you physical data like any variable of motion. So anything you do in quantum mechanics, you have to. That means it is almost more like doing some more few more steps of mathematics. So today it will be more prominent because we'll be actually solving a problem. The problem was introduced last day. Oh, this is me. Okay, and mantra is simple. Okay, we consider wave nature of the matter. Okay, these things you know, and these are the postulates I was talking about. Okay, postulates of quantum mechanics. So these are ready for us. So the problem one I actually presented in front of you, wherein this equation of Schrodinger will be solved. We will be solving Schrodinger equation. We will be solving the equation of Schrodinger. These are the list of operators which are very essential for our discussion to continue. The concept of the operators. For every variables I wish to measure, there exists an operator, and the idea of operator makes the time independent version of the Schrodinger equation as an energy eigenvalue equation, as you can see there. Okay, now after that I presented the problem one in front of you. Problem one of quantum mechanics is basically the problem of electrons moving in a metal. So the scientist Paul Drude in 1900 tried to explain why metals are good conductor. Okay, he tried to explain why metals are very good conductors of electricity and heat. So he has set up, that means in a metal electrons move more freely. So why metals in a metal electrons move more freely? So in order to explain that, he has set up a theory taking the idea, because at that time no quantum mechanics was there. He has taken up the idea from thermodynamics. Okay, that in a metal that is called free electron theory. Electrons move freely just like the molecules of the gas moves freely. If large number of metal electrons are moving, so if you keep the metal at a temperature T, the electron will be experiencing so it will have some kinetic energy 3/2 kT. So with that it will move randomly. Okay, and this entire theory, as I mentioned, is called free electron theory, considering that free electron means the valence electron which has the license to participate in all types of interaction. So that means any metallic system is therefore any metallic system is therefore a core which is made of the nucleus and the core electron. So it's a positive ion core. For example, you can see the sodium, 11 unit of positive charge in the nucleus, and 10 core electrons ultimately gives a positive ion core, which is consisting of 10 electrons, 11 protons, 11 neutrons, and many other particles whose individual mass is much larger compared to the mass of a single electron. So it is thought that any atom means a static immobile charge, positive ion and free electron. Electrons have got the license to move freely. Okay, so these electrons are all moving randomly, freely, and in the entire theory, just like the molecules of the gas moves randomly, so that idea was used. So no other so all interactions, if everybody moves randomly, there will be collision. So the only interaction is mechanical. Okay, so they are all colliding like the way as you can see in the picture. So they are all colliding. Now this idea is that if an electron is here, it will be colliding. It will be, if no electric field is there, no velocity will be generated. Finally, average velocity will be 0. And if some electric field is there, what would happen? If some electric field is there, what would happen is that under electric field it has to move in a direction opposite to the field. So ultimately some net velocity will be developed. That is called drip velocity. Now this idea was good enough to explain the current flow in a metal. Ohm's law can be achieved. So these are the success stories of the Drude's model, but you see it is only restricted to metal. So Sommerfeld has to come into business to provide the theory called series free electron theory. So all the basic framework is same, excepting only one little change. In 1920 he is doing it, so quantum mechanics was there. So electron is not a matter, not described with it with the way Drude did it. Electrons are moving, colliding, etc., etc. They are all right, but he used probability interpretation. That is, electrons, I cannot see the electron. I represent electron with the function psi, probability of finding the electron given by psi square. So that idea was utilized. So electron is moving between the two ions according to my picture. So probability of finding the electron will be non-zero between 0 and a. X equal to 0 is the position of the first ion, second x equal to a is the position of the second ion. Okay, and so that is across the mean free path of length a, it is moving. So between 0 and a, probability of finding the electron will be non-zero, else it is 0. So now I am presenting the problem as a quantum mechanics problem. So because I am expressing it in terms of function psi. So we'll explain the electronic journey from 0 to a, that means one of the linear path, that is called mean free path. Mean free path means free means no force acts on the particle in between that journey. Effective force is 0, no potential energy will be there. But what the problem to the electron? It is trapped between 0 and a. So as if two ions are there, it is creating two barriers, walls in front of the electron, so not allowing the electron to go away. So those two ions are playing the role of two infinitely high wall. So the situation is that a particle is trapped between two infinitely high wall. So you have to describe this problem, how a matter, what happens if a matter is trapped between two infinitely high walls. So how do I describe that motion? To describe the motion, it's a quantum mechanics problem. So you have to know the psi, because psi is non-zero only between the 0 and a. So you'll be calculating psi now using the equation of Schrodinger. Okay, so let us do it. Okay, and Schrodinger is going to help us. Okay, so this is the actual problem. A particle is moving between 0 and a. X equal to 0 is the position of the first ion, x equal to a is the position of the second ion. Chance of finding the particle outside this region between 0 and a is 0. So at x greater than a, it is 0. At x a equal to a, their ion is there, matter cannot be there, psi square will be 0. At x equal to 0, ion is there, particle electron cannot be there, so psi square is 0. At x less than 0 also psi square is 0. So where the matter is, the particle is between 0 and a. So its mod psi square is non-zero between 0 and a. Okay. So these are the values of psi. If mod psi square is 0, psi is also 0. So it is 0 for x greater than equal to a and less equal to 0, and non-zero only inside the between the two ions along the mean free path according to the previous description. And why it is restricted to move this? Because of this potential energy barriers at x equal to 0 and x equal to a. Between 0 and a, no force acts on the particle because it is mean free path, so v is 0. So this is called description of the problem. So now we have to solve this as the Schrodinger equation, okay, for getting psi. Now you see, if I solve this equation of Schrodinger, I will get psi. That is my objective. But I know psi will be 0 for x greater than a and x greater than equal to a, as I have shown there, and x less than equal to 0. So if I know the value, why should I solve an equation? You see, solution of a problem is a mathematical hazard. Solution of a differential equation is a mathematical trouble, mathematical hazard. So why should I take that hazard if I know the value of psi? If I do know the value of psi, I know the value of psi, it will be 0 outside that well. This is called one-dimensional infinite potential well problem, because the matter is in a well of energy. Okay, in a well of potential energy. Okay, and height of the wells are infinite. Because the matter cannot go out of the well, so psi is 0 outside the well, and between 0 and 8 is non-zero. So if I have to solve the equation, if I to take that mathematical pen, I should only solve it between 0 and a, where psi is non-zero. I do not know the value of psi, but I know it is non-zero. So we will not solve the equation for x greater than equal to a or less equal to 0, where it is non-zero. And you solve it between 0 and a. Good news is that where psi is non-zero, you see v is 0 there. So your equation becomes very easy. Okay, the second term involving potential energy in the right hand side goes to 0. So your life is now easy. Okay, if you put v equal to 0, it is a very simple equation to solve. So now let me solve it in front of you, because a lot of steps are involved in examination. It comes as a full maybe 15 marks, 12 to 15 marks question. So please carefully go through the steps. Okay, please get it. Let me do it for you. And this is called one-dimensional infinite potential problem in quantum mechanics. Okay, this is called one-dimensional infinite potential problem in quantum mechanics. Is the first problem of quantum mechanics for you. A particle of, this is a general statement of the problem. A particle of mass m is moving between is restricted to move between x equal to 0 and x equal to a. At x equal to 0, it is facing an infinitely high potential energy barrier or two walls. At x equal to a is also another infinitely barrier. So potential energy is infinity at x equal to 0 and x equal to a. So equivalent to those two ions in my problem. And so probability of finding the particle outside the region x greater than a is 0, psi is also 0. Here also x less than 0 is also 0, psi is 0. Psi is non-zero only between 0 and a. So psi square non-zero means psi is also non-zero. We also thought between 0 and a no force acts on the particle, it is free particle, so potential energy is also 0. So considering psi as the probability function, so this is the way we are describing the problem. So this description, as I have written here, okay, that it's the same thing. Between 0 x equal x greater than equal to a means here greater than a and equal to a, here potential energy is infinity. So if you think in terms of ions of the last problem, ions are there, electron cannot be here. So here psi square is 0. So psi is also 0. So at x equal to 0, psi square is 0, psi is also 0. At x less than 0 also, psi square is 0, psi is also 0. So where the particle is between 0 and a. So here psi square is non-zero, psi is also non-zero. Why it is happening? Because V is infinity at the two boundary at x equal to a and at x equal to 0. Okay, at the two boundaries V is infinity. So now this is called the description of the problem. So V is non-zero. This is called description of the problem. Now my job is therefore to find out, solve this equation to get the function psi. So if I solve the equation and get the function psi, you see, as I mentioned few minutes back, we are solving it only for the region x 0 and a, where psi is non-zero and v is equal to 0. So this term goes to 0. So the equation becomes this, like this much, d to psi dx2 equal to minus by 2 mu h cut square psi. So next, where a is 2 is a constant, m is a constant, e is a constant. So this become d to psi dx2 plus 2 by h cut square psi equal to 0. Now this quantity is called k square equal to constant. K square equal to 2 by h cut square is a constant. 2 is a constant, mass is a constant, E is constant by the basic definition of Schrodinger equation, which is expected to give me the energy. H cut means Planck constant by 2 pi, which is another constant. So this equation, if you consider this as k square, so this equation therefore takes a form like this much, d to psi dx2 plus k square psi equal to 0. Now this is, if you look at this equation, it is an equation of a harmonic oscillator. How do you solve this type of equation? We assume psi is equal to a to the power mx kind of thing. If I do the replacement, we get this much, m square plus k square equal to 0, which gives me m equal to plus minus ik. So if you look at the solution, it becomes psi equal to a1 e to the power plus ikx plus b1 e to the power minus ikx, considering a1 and b1 are integration constant. So you have got my psi. So now, so therefore if I look at it, we may now write down, so this is my k, we may now write down the solution of this equation is therefore psi is equal to a1 e to the power ikx plus b1 e to the power minus ikx. This can be written as cos kx plus I sin kx, and the next one can be written as cos kx minus I sin kx. So if I put all the cos term together and all the sine term together, so psi is basically a1 plus b1 makes another constant a cos kx, and ia1 minus ib1 makes another constant, say b sin kx. So this is my psi. Now question is that, is it obtained? Answer is that it is not obtained, because a and b are integration constant. To get this a and b, from basic mathematics, to get a and b, we have to apply boundary condition. We have to apply boundary condition. Where is the boundary of the problem? Boundary is here at x equal to 0, at x equal to a. So boundary condition is that at both the points, both the ends, psi is 0. Psi is non-zero only between 0 and a. Between 0 and a it is non-zero. Okay, else everywhere it is 0. So basically, so if I apply those two boundary condition, so my value of would be like this much. Psi is basically is like this much. A cos kx plus b sin kx. Boundary condition 1 is that at x equal to 0, psi is 0. That gives me left hand side of this equation is 0, a into 1 plus b into 0. So this makes a equal to 0. So the this coefficient cost term goes to 0. So this equation of psi is reduced only to the sine function. To get b, you apply the second boundary condition. Second boundary condition is that at x equal to a, psi is 0, which gives you b sine k equal to 0. Two options are there, either b0 or sine function is 0, because left hand side is 0, but b cannot be 0, because if you make b0, sine function psi will be vanish, but I know psi is non-zero here. So only option is that sine function is 0. So write down for acceptability of a function, therefore, otherwise a function will become 0 everywhere. But I know matter is there. B cannot be 0, so only option is that sine function is 0. Sine k is 0, which means sine n pi, where n is a number 1, 2, 3, etc. Okay, 0, 1, 2, 3, etc. actually, theoretically. So k equal to n pi by a. So I've got k. So if I replace the value of k equal to n pi by a, my psi is still b is not known, but I get the value of k, that is n pi x by a. Understand? So now I have to still my b is unknown. To get b, use normalization condition. That is total. You see, if you look at the problem, this is my potential well. This is x equal to 0, x equal to a. Probability of finding the particle is non-zero here, and elsewhere probability of finding the particle is 0. So I know particle is between 0 and a. So total probability of finding the particle in this region has to be equal to 1. So that idea, I'll utilize this. Total probability of finding the particle, any particle in universe is 1. That utilization, that idea I utilize, that is minus infinity to plus infinity. Mod psi square dx equal to 1. So I divide the limit into 3 parts. Minus infinity to 0 means this region. This problem I have already solved you in your class. Mod psi square dx plus 0 to a, that means this region, plus a to infinity, the right hand side of this is a to infinity. What minus infinity to 0 means this region 1 say. So here psi is 0. A to infinity means region 3 say. This region. So here also psi is 0. Only between 0 and a, psi is this, here psi is non-zero. And that value we have achieved is this much, 0 to a. So far I have got this much, mod b square sine square n pi x I dA, a dx. Now right hand side is 1. If you put the value of this, will be mod b square by 2. It will be 2 sine square theta means 1 minus cos 2 n pi x by x dx. Right hand side 1. Integration of cos term is 0, and integration of this is a. So mod b will be from here on is root 2 by a. So you have got mod b. That means you have got psi. What is psi? That was b sine of n pi x by a. This is root 2 by a. Root 2 by a sine of n pi x by a. So you have solved Schrodinger equation and you have got our psi. So therefore, if you write down it in a fair way, proper way, that if this is my one-dimensional infinite potential wave problem, the wave function here psi is equal to root over 2 by a sine of n pi x by a, where n is a number 0, 1, 2, 3, etc. Now, if you make n 0, psi will vanish, so n can't be 0. So n equal to 0 is this solution outside the region x greater than a, x less than 0. Here, this is the n equal to 0 solution. X equal to 0 because psi is 0 here. X equal to a. In between the region greater than 0 and less than a, in between this region, my n value should be other than 0. Okay, it start from 1 and beyond. Okay. So basically, another thing is that if you change n, suppose psi n1, that means psi pi x by n to another value n to another value. To show the independence, I call it psi nx. Now, another information, so we have obtained the wave function. Wave function is there, you have obtained it. Now, another important information that you can generate also, that is the calculation. You see, I told you Schrodinger equation is an energy eigenvalue equation. So if you solve it, you will not only get the wave function, but you also get the total energy of the system. So you can get the total energy of the system because of with the help of the equation that is already kept for you. That is, this is my problem. This is x equal to 0 and this is x equal to a. This is my psi. But when I was applying those boundary condition, I get from the second boundary condition k equal to n pi by a, n equal to 1, 2, 3, etc. And when I was doing the conversion, I have also written k square is equal to 2m by h cat square. So you can, if you mix this equation, suppose this is equation 1 and this is equation 2, these two equation in k, I will get an expression of energy. So calculation of energy of the system. So what you have to do, you have to write down k square equal to 2m by h cat square. You replace k square with that expression. If you do the replacement, it becomes n square pi square by a square equal to 2m by h cat square. So this gives you n e is equal to n square pi square h cat square by 2m square. So this is the energy of the particle. If it is, this is energy is given by En, therefore, because it depends on n. N is 1, 2, 3, etc. So you see, idea is that for every n1, there exists one energy and one psi. So let me show you how the value of n actually influences the value of E and psi. So get it. Suppose I choose say n equal to 1. So this is the value. Psi nx is equal to root over 2 by a sin n pi x by a, and En equal to n square pi square h cat square. This equation will come when we'll be solving nanomaterials classes problem also. Okay, 1, 2, 3, etc. Suppose I choose n equal to 1. So your corresponding energy is pi square h cat square by 2m square, and our function is psi 1 equal to root over 2 by a sin pi x by a. If I choose say n equal to 2, your energy, this will be 2 square, that means 4 pi square h squared square 2m square. This is nothing but 4 times c1, and our function will be psi 2 equal to root over 2 by a sin 2 pi x by a. If you make n equal to 3, so E3 will be equal to 9 times E1, and energy will be psi 3 equal to root over 2 by a sine of 3 pi x by a. So you see, energy levels are discrete, and that is the beauty of quantum mechanics. According to Drude, the energy of the particle was 3 by 2 kT. So if you use the Drude model, so if I plot the energy according to Drude's model, all energies are right, all energies are allowed. Drude told all values of energies are allowed. There is nothing is forbidden, all are allowed. This is the Drude's idea. But what Sommerfeld is telling, because of quantum mechanics, not allowed, all the values are allowed, only some discrete values are allowed. These discrete values are allowed. Okay, that is the beauty of quantum mechanics. Okay, so energy of the particle will be discrete, quantized, which was told long back by Max Planck also. Now another important question that comes in examination is to plot the wave function. So wave function, you know, is given by this much, root over 2 by a sine of pi x by a. sorry, n pi x by a. So basically it depends on n. So for n equal to 1, suppose I want to plot the wave function corresponding energy, you know, this is the expression of energy, n square pi square h cut square by 2m square. Okay, so this is for n equal to 1, it is pi square h cut square by 2m square. So psi 1 is the wave function here, root over 2 by a sine pi x by a. If you see, I know this is x equal to 0 and this is x equal to a. Outside this 0 and a, this is x equal to a. At x greater than a, I know psi will be 0. At x less than 0 also, I know psi will be 0. So it is, I will have to plot it between 0 and a. So if I plot it, say at x equal to 0, you know, sine function is 0. At x equal to a, sine function is sine pi 0. So this is at say x equal to a by 2, sine pi by 2 will be 1. So if we plot the wave function for x, you see this is your energy, this is your wave function. Suppose I consider say n equal to 2. So your wave function, your energy will be equal to E2 equal to 4 times E1, and your function will be psi 2 equal to root over 2 by a sine 2 pi x by a. You can now see if you do the same thing just like this, at x equal to 0 it is 0, at x equal to a it is 2 pi 0, at x equal to a by 2 also it is sine pi 0. Now if I choose x equal to a by 4, it is sine pi by 2 again, so it is positive. Now if I, this is a by 4, if I, so a by 4, this is 2a by 4, suppose this is 3a by 4, 3 pi by 2 means it is negative. So if I plot it, it is almost like a normal sinusoidal wave function. Now if you plot it in the energy scale, this is the lowest energy state, this is the next one. So this is a ground state for the particle in infinite potential, which is almost like a half of a sine wave, and this is the first excited state, which is like an actual sine wave. I was showing this initially when I was introducing concept of psi, etc. Now let me show you another case. Suppose n equal to 3. Actually, you can do it also yourself. N equal to 3 means energy is 9 times E1, and psi 3 will be equal to root over 2 by a sine 3 pi x by a. So if you put it at x equal to 0 and pi, it will be 0. At here it will be negative 3 pi by 2, a by 2. And in between, if you plot it, the graph would be looking like this much. So basically these are the wave function of the particle for second excited state. So these are the various energy state or electronic wave function, or the wave nature of the matter electron, probability waves of electron when it is in lowest energy state or in higher energy state. Now suppose one last little case let me discuss in this regard. Suppose I have got a particle electron is so far in my discussion between 0 and a, only one electron was moving. So as I have shown you, the lowest energy state is there is n equal to 1, E1 is pi square h cut square by 2m square, and my function is, we have got it, okay, root over 2 by a sine pi x by a. Suppose I have got 100 electrons here. If I have got 100 electrons moving, it's a law of nature, majority of them will occupy the ground state as a wave function. So this should be the prepared wave function. So if I plot a function, so probability of finding the electron will be highest at a by 2. So at a given point of time, most of the electrons should be at a by 2. So this will be on an average position of those 100 electrons at a given time. So only this is the average value in quantum mechanics is called expectation value. So I can show you it mathematically also. Expectation value of position, if we calculate it also, it will be a by 2. I did it in your, when I was teaching you expectation value dx. So if I divide it into 3 parts, minus infinity to 0 means here psi is 0, you know. Zero to a psi star x cap psi dx plus a to infinity psi star x cap psi dx. Now in this region psi is 0, here also psi is 0. So basically your problem is restricted only between 0 and a. 0 and a psi star is basically, this is your psi. So we are only happy with the ground state of function psi 1. So root over 2 by a sine pi x by a, x cap is x, root over 2 by a sine pi x by a dx. 2 by a is 2 by a. 0 to a x sine square pi x by a dx. So if we bring this 2 inside, this is 1 by a 0 to a x2 sine square theta will be there, which will be 1 minus cos 2 pi x by a 2 sine square pi x by a dx. So if I utilize further, this is 1 by a 0 to a x dx, 0 to a x cos 2 pi x by a dx. Second term will be 0 by orthogonality condition, and the first term is going to give you x square by 2. So this is 1 by 2 s square by 2 means result of this average value calculation would be a by 2, and that is what you see, average position of the particle is a by 2. So this completes our problem 1 of quantum mechanics. Okay, let me get back to the PowerPoint a bit. Okay, we have completed the problem 1 of quantum mechanics. Okay, it's over. We have, these are the major outcome, that is a electronic wave function, and a modular size square is also plotted. Okay, you see, so beautiful pictures are there. Ground state is half sine wave, that is the mod size square, probability is most at a by 2. So the first excited state is the sine wave. You can see the probability per point. The variation of probability of finding the particle, it is higher probabilities at two ends, a by 4 and 3a by 4. In the second excited state is a higher probability at a by 4, a by 2 and 3a by 4, and like this. Okay, and energy is n square pi square h square so by 2ms square. So this is the calculation of the problem, and these are the variation. Okay, this picture is a very common and familiar picture to you. Now I have been showing you now the actual problem I have done. Okay, so beautiful problem. So if the matter is moving, its wave functions are shown. The first one is ground state, second one is, okay, you can see the picture A is the particle moving between two infinite wells. Picture B is the plot of the is a ground state wave function. Picture C is first excited state. Picture D is second excited state. Picture E is third excited state. Picture F is a fourth excited state, like that. And that is the corresponding probability waves you can see here. So now this is the conclusion of one-dimensional potential wave problem, infinite potential wave problem. Our next problem is the junction diode problem, which is another wonderful problem. So wait for that. We'll discuss it in the next lecture.